Hello, this is a short video as a pre-lab lecture for the Purification by Crystallization experiment in Chem 102. And our goal today is to purify a mixture of two solids. And the compounds that we're dealing with are, one's called alum, which is a common name for kind of a weird salt. It's got both the potassium ion and an aluminum ion, potassium +1, aluminum +3, and sulfate. So sometimes it's called potassium aluminum sulfate, but alum's just a lot quicker. It also includes copper 2 nitrate. Copper 2 nitrate is kind of a bluish green color. Alum is white. And when you look at the initial solid or initial sample, that's a mixture of these two, it's kind of a blue-green. And hopefully by the end we'll have purified a white solid, which should be fairly pure alum. So crystallization as a means of, and separations of mixtures is really an important part of what chemists do. I had a friend who said, there's one section of chemistry is called analytical chemistry, and analytical chemists, pretty much all they do is, one is analyze, figure out what's in a sample. That's, sort of the name implies. But the other one you might not think so much about is they separate, and they're really interested in ways that you can take mixtures of things and separate them. And sometimes that's so you can separate the components and then use one of the components specifically in a different application. Sometimes it's just to do the analysis part. If you want to figure out what's in a mixture, oftentimes the first step is to separate into individual components. So separations are really important for chemists, and we're going to do this is sort of an oldest and one of the simplest types of separations. And this is a separation by crystallization, and it depends on having some difference in solubility between the compounds being separated. Usually what's going on is you take a sample that's a mixture. Here we got little gray dots, little red dots, and we want to get rid of the red dots. So we'll take that sample, put it into a solvent, and dissolve it, often with heating. And then as we cool it down, we want to find a solvent such that one of the components will precipitate at lower temperatures while the other one will not, will stay in solution. And that's how we're going to achieve the separation. So here in this example, the little red dots and the gray dots, they both dissolve at higher temperatures, but when we cool down, only the gray dots precipitate out as a solid. And then we can collect that solid, and we've got a hopefully purified solution, or purified solid. So in our experiment, how are we going to do this? Well, this figure over here kind of should hopefully illustrate. And the big thing we want to pay attention to is that at low temperatures, the alum has a very low very solubility. It's at 5 degrees, it's around 3.5 grams per 100 grams of water. But copper nitrate still has a fairly high solubility. It's maybe around 70 grams per 100 grams of water. But if we heat up, if we go up to like between 80 and 100 degrees, we can see alum it's fairly soluble. I estimated around 70, 80 grams per 100 grams of water. And copper is really, the copper nitrate is really soluble. So what we can do is take our mixture of these two compounds, heat it up in water, everything will dissolve. But then when we cool it down, the copper nitrate will stay soluble. Most of the alum will precipitate, not all of it. We do see that there's some alum that dissolved at 5 degrees. Not a lot, but some. But we're willing to lose a little bit of the sample in that process. So how does this procedure work? Well, just like I said, you're going to dissolve the solid in water with heating. You're going to cool it down. We're going to use ice to cool it down. Ideally, to get the best separation, you want to let it cool slowly. If you cool it down really quick, there is some tendency that the crystals of the alum will maybe trap some copper nitrate in the process of crystallizing, but we don't have all day for this experiment, so we will use ice to cool down our sample and get it really cold. Once it's cold and we've precipitated the alum, we're going to isolate the solid with something called vacuum filtration. And vacuum filtration uses this thing called a Buchner funnel. And this is a little plastic funnel, and you can't see it, but there's this lower plate here has small holes in it, and you put a piece of filter paper on top of it. And then you put it on top of this thing called a filter flask. And a filter flask is just a flask that has a little glass arm pointing off to the side. And you can hook up a tube and attach it to a vacuum. And we do that just because we want to be able to, oftentimes with the solid, it can kind of block liquid from going through the filter paper. And so to speed up the process, we use a vacuum to pull air through and liquid through this funnel. So the Buchner funnel is this particular setup that allows to vacuum filter solid and liquid and separate the liquid from the solid in this manner. When it's on here, we're going to wash it with a little bit of cold water. The cold water will lower the amount of alum that dissolves in the water that goes through it. And the wash is just if there happened to be some copper in the solid that precipitated, this would help to wash that out and kind of clean up the alum. And then we're going to dry it. We're using the same setup. So this setup can be sort of like, imagine a very windy day. If maybe nobody does it anymore, but if you hang your clothes out to dry on a clothesline, on windy days, there's lots of air moving over those clothes, and they will dry more quickly because the air is not saturated with water, and it comes and goes over the clothes, and some of the water is transferred from the clothes to vapor that the air carries away. Well, if we have a vacuum system here and we just leave it on, air will just be continuously being pulled over the sample, and it will be carrying away water vapor as that takes place. And so we leave it to sit on there for about 15 minutes, and that'll dry out the solid. So we can, when we weigh it at the end, we just weigh the solid. We don't weigh some water that's attached. That's part of the solid, attached to the solid. So we are interested in how much of the alum doesn't crystallize. So one of the things we want to know is how much alum is in our solid, and we also want to isolate as much of the alum as possible. And to do that, accomplish these two things, first off, we're gonna keep the volume of water to a minimum. So when we dissolve the sample at the beginning, we want to do just as much water as necessary. We don't want to use a whole lot of water. And when we wash the solid with cold water, when it's on the Buchner funnel, we want to use just as minimum amount of water. And then we'll measure how much water was used to dissolve and how much to wash. We'll measure that entire liquid, and that will tell us how much of the, if we know the volume of the water and if we know the temperature of the water, we can figure out how much alum was dissolved in that water. So here's how we're going to do it. So after the sample's been filtered, using a graduated cylinder, we'll measure the volume of the water that was used to dissolve and wash the sample. And we'll measure the temperature of the water just before we do the filtering. And the idea there is that at that point, we should have reached an equilibrium where a certain amount of alum will be dissolved in the water, and we can use the solubility at that temperature and the volume to get the amount. So in your lab manual, you should see this table, and it shows how the solubility of alum in 100 milliliters or 100 milliliters of water, how it changes. It's in this region, it's fairly linear, and we're going to assume that it's linear, maybe up to 5, 6, 7 degrees, something like that. But if you notice, each of these entries is 3 plus a couple numbers after 3, and those numbers are the same as the temperature. So like at 0.0, it's 3.00, and 0.5, it's 3.05. And at 2 degrees, it's 3.20. So you can sort of see the tenths number is the temperature in degrees, and the hundredth is the temperature in tenths. Now, that's entirely a coincidence. There's no reason that that has to be. It's just we're going to take advantage of that while we're working with alum. It just works for alum and water, and there's no big meaning to it. Just happens to occur this way. And so if we say we use 32.5 milliliters of water and the water was 4.3, we're going to say, well, the solubility of alum in 100 milliliters of water should be about 3.43. This is probably a little bit of an estimate, but it's a good estimate, and so we might as well use it. And so to get the amount of alum left behind in the water that was not precipitated as a solid, we just take the product of these two, 32.7 times 3.43, divide by 100 milliliters, and we get that. In this case, we would have left 1.12 grams of alum dissolved in the water. Next, you calculate the percent alum in the sample. So it's mass percent. We just take the mass of the crystallized solid, so the solid that crystallized, but we also take in that number we just calculated, or a similar one. We take in how much of the alum was left behind as dissolved. And we add those two together, divide by the mass of the sample, and then you multiply by 100%. And if this was done in class, everybody would have the same sample, or they would have samples taken from the same batch, and so they should all have the same percent alum, and then we compare those, and we're going to do that to do some data analysis. And one of the parts of the data analysis is something called a Q-test. And so a Q-test is a way to look for outliers in a set of data where all the data points are thought that they should have the same value. So if you have measurements of the density of something, or here the percent alum, and a bunch of people make measurements of that property and compare them, and maybe one of the values seems like way off compared to the other ones, and the Q-test is a way to sort of to see if that's the case. So what you're going to do is you have an outlier that you wonder, can I disregard this? And the way you're going to do that, or the way you're going to figure that out, is you calculate something called Q-calc. And Q-calc, you take the absolute value of the difference between the quantity the data point you're interested in and the next closest data point. And then you divide by the range of the data. And this gives you some number. It's going to be less than 1 because the range of the difference between an outlier and the next closest can't be bigger than the range of the data, which is the difference between an outlier, the one extreme, and the other extreme. So it's going to be a number less than 1, and we're going to compare this Q-calc value to a table. And the tables are generated by sort of statistical analysis of how errors pop up in random errors pop up in experimental measurements. So we're going to compare Q-calc with a value from a table of Q values. And if Q-calc is greater than the Q table value, then we can reject that piece of data. So here's an example. So imagine we have 10 data points. The largest value is 22.5, the next closest is 19.3, and the range is 4.2. So the smallest value has to be 18.3. So we calculate we calculate Q, and we see that its value is 0.74. Then we have to go over to this Q table, and this is a Q table for rejection at 90% confidence. And then we say we have 10 data points, so we have to look down here to the entry for 10 samples, and we see the Q value is 0.41. And 0.74 is greater than 0.41, so we can reject that data point with 90% confidence. Now we go and so we say, okay, that data point is an outlier. We are 90% confident it's an outlier. That value is not due to a random area. It's due to some non-random process process that took place during that measurement, and it skewed our results, and we can reject it. So now you're going to test the next largest value, 19.3. So then here it's going to be different. The range is going to be different because we said, before it was 4.3. The range is only going to be like 1 because we said if the range is 4.2 and the largest value is 22.5, the lowest value is 18.3. So the range changes, but this changes on here too. We're going to have 19.3 and the next closest value, which is probably going to be a lot closer. The 9 data points only lie between 19.3 and 18.3. And so there's a higher probability that we're going to have a Q value less than 0.41, and therefore we can accept the data. You want to test the upper limit, the upper data point, but also you want to test the lower data point. I haven't showed that here. So you should also go through and do this same process where you take the smallest value and minus the next to smallest value, take the absolute value, and then divide by the range and test that with the Q test. All right, in summary, we separated a mixture of alum and copper nitrate based on dissolving in hot water and crystallizing the alum at a low temperature. Need to keep the water used at a minimum, and some of the alum will be lost in the cold solution. And that's sort of a too bad, but just can't be avoided. I'm going to calculate the mass percent of alum in the sample and use the Q test. Good luck with your experiment.